Okay, we're continuing with example problems on limits of series. And by limits of series, that just means we're evaluating infinite series, infinite sums, to see if they converge or diverge. And if they converge, that means that the infinite sum equals an actual value. So what is that value? If they diverge, then how do they diverge? Do they diverge to infinity or negative infinity or oscillating? Okay, and so what we've been talking about is that when it comes to analyzing any series, but also we're focusing on infinite series, it's really valuable if you can get the corresponding S sub n formula for that series, to where the S sub n is valid for all n, going from the start point to infinity. Because if you have that formula, then you have everything you need to analyze the series. You can just take the limit as n goes to infinity of that formula, and if it converges to a value, that's the sum. That's the infinite sum. If it diverges, then it'll tell you everything you need to know about the divergence. But it's not that easy. In general, it's not that easy to get to find an S sub n that's valid for all n. We saw how we could find an S sub n for the arithmetic and the geometric series, but the textbook also showed an example of how if you have what's called a telescoping series, you're able to find an S sub n for that series. And so in this video, we're going to work some examples of series that are telescoping. So, okay, determine whether the series is convergent or divergent by expressing S sub n as a telescoping sum. If it is convergent, find its sum. All right, so what we want to do first is we want to split this up into two separate fractions using partial fraction decomposition. So all right, so now there's the form of the decomposition. Let's clear the fractions. So we've got 1. Okay, so when n is equal to 0, you've got a is equal to 1. When n is equal to -1, you've got b is equal to -1. So, okay, what we've got is okay, plus okay. So what we're going to do now is we're going to write this series out like in that expanded form. So okay, we're going to write out the S sub n. And so the S sub n is, so when n is equal to 1, we've got 1 over e plus 1 minus 1/2 plus when n is equal to 2, we've got 1 over e squared plus 1/2 minus 1/3 plus, let's do another term, so 1 over e cubed plus 1/3 minus, okay, plus, okay, and what I want to do is do the n minus 1 term, just so we can get a good picture of this. Minus, and then n minus 1 plus 1 plus, and then the nth term. We're just doing the nth partial sum. We're not going off to infinity. Right, so we end here. This is it. This is the S sub n, okay? And so what happens with a telescoping series is that like you get a bunch of middle terms just like subtracting out. So like this subtracts out, this subtracts out, and then you would have like, so there would be this would subtract, this would subtract out with something over here. This would subtract out with this. This would subtract out here. And so what you can see is that the E terms don't simplify. And so what we can do is let's separate this into two separate sums. So, okay, we're just focusing on the S of n for now. So we can do, based on properties of summations, so we'll have to, let's change this to I. I know it's kind of confusing, but this is still, this is still the same thing. So 1 over e to the I plus, and okay, but this is the idea. This infinite sum here, I mean, let me write it out. Okay, because it's telescoping, we know what this formula is. So we've got, this doesn't change. Okay, we know this, we can see it's just going to be 1 minus that's what this is equal to. What is that saying? If you want to sum, we're just looking at this as a summation. If you want to sum the first 1,000 terms of this, plug in 1,000 into this, and that's the sum. You see? Like, this is the S of n for all n going to infinity. This is it for this. Okay, but we still have this here. Okay, now we saw this is not telescoping, so what do? Well, there's only one other method we've learned so far to find an S of n, and that's if we have a geometric series, and this is geometric. We can take out the I, we can write it this way. Okay, but it's not in that form where this is to the I minus 1 where we can see what the first term is, but we see the common ratio is 1 over e. So what's the first term? When I is equal to 1, the first term is 1 over e. So we have A is equal to 1 over e, and R is equal to 1 over e. Okay, what is this equal to, though? Okay, so what is the nth partial sum of a geometric series? Well, we can just go to the textbook. Okay, here it is. This is what we derived in the algebra video on geometric. It was sequences. We derived this. I forget what it was. The geometric sequences or in series video, but we also derived this in the section of the textbook. And remember, this is not the infinite sum formula. This is the S of n, the partial sum formula, and so that's what this is equal to. With A is equal to 1 over e and R is equal to 1 over e. So what we've got is 1 minus and then we would have, so E, right, plus 1 minus, and there we go. There is the S of n for this series. Okay, so there's the S of n. Now we could simplify this to make it more presentable, but just to save some time, all we need to do, let's just go ahead and take the limit of this. So we can go ahead and answer this question. Okay, so, well, all right, this we know is going to, 1 over e is the common ratio, and that's less than 1. The absolute value is less than 1. So we know what this is actually going to converge to. This is going to be a over 1 minus r. That's going to be this limit. Okay, this limit goes to 1. What does this limit go to? This goes to 0. Okay, so there we go. So, okay, we've got e minus 1 over e over e times, okay, There we go. So this sum is equal to, it converges and it's equal to that. And actually we can simplify this, make it a little bit cleaner. So this is, so 1 minus 1, yeah, e, there we go. Okay, same idea. Let's separate this into the sum of two terms. So we factor the denominator. All right, now, okay. All right. So we've got, all right, so when n is equal to 1, okay, when n is equal to minus 1, oh wait, no, this would be 1. Okay, so what we've got is, we're starting at 2, and that's not a problem. And then, so we'll write it n minus 1 okay. So now the idea is we want to write out the s of n, like expanded out. But we start at n is equal to 2. So, okay, we've got 1 minus 1/3 plus, now n is equal to 3, 1/2 minus 1/4 plus 1/3 minus 1/5 plus, let me do one more, 1/4 minus 1/6 plus, okay, and then we can do the n minus 1th term. So n minus 1 is n minus 2, n minus 1 plus 1, okay, and then the nth term. Right, so I just put n minus 1 into here. N minus 1 is n minus 2, n minus 1 plus 1 is n. All right, so, okay, again, this is s of n. This is not the infinite sum. This is just like the partial sum. All right, now it's going to be telescoping because there's a lot of canceling that goes on in the middle, and you're just left with like a few terms from the beginning and a few terms from the end. So, okay. Okay, so actually, let's just, so we can see this, let's do this. So, plus 1/5 minus 1/7 plus 1/6 minus 1/9, okay, like that, okay? So, there goes the 1/5, and there goes the 1/6. All right. So yeah, this is definitely a little bit confusing. It looks like we're staying with the 1 and the 1/2 no matter what. Now, what terms do we stay with in the end? So every single middle term is going to cancel out. So this is, the 1/9 is going to cancel with something over here. Okay. Now, if we look here, none of these are the same. All right. Well, okay, let's do this. What is putting in n minus 2? N minus 2 minus 1 is n minus 3. N minus 2 plus 1 is n minus 1. Okay, so this goes away. We know this is going to cancel with something. This is going to cancel with something. And this, the n minus 2 here is going to cancel with, so like, imagine this is the n minus 2. That's going to cancel with a term over here. So now actually so we can see this clearly. Let's write this. I think this is tough. This one's kind of tough to see. Let's do this. So okay. So we've got 1/5 minus 1/7, okay, plus 1/6 minus 1/8. All right, now what I want to do is let's go like all the way back to, let's start with n minus, this is the nth term. Let's go to the n minus 1, n minus 3. So n minus 3 minus 1 is n minus 4. N minus 3 plus 1 is n minus 2. Right? Plus, now the n minus 2 term, n minus 2 minus 1 is n minus 3. N minus 2 plus 1 is n minus 1. Okay, now the n minus 1 term, n minus 1 minus 1 is n minus 2. N minus 1 plus 1 is n plus, and then the nth term. Okay, so we can really see this expanded out clearly. So there goes the 1/6. The 1/5 cancel here. Now this is where it gets a little confusing. So we can clearly see that once we get to like the true middle of all of this sum, that terms are going to be fully going away. It's not like we're in the, you know, if we're going out to like 1,000 S of n going, if we wrote this out with 1,000 terms, when we're really in the middle, terms are just going completely away. But at the edges, it's kind of confusing. So it looks like we're going to be left with the 1 and the 1/2 here. Now, but what happens? It would seem like we're going to be that these two terms should fully cancel. So like, okay, the 1/7, we can't see it, but it's going to cancel with a plus 1/7 over here, and then the 1/8 is going to cancel with a 1/8 we can't see. So we know those are going to cancel. Okay, now, so, all right, we haven't gotten to the edge yet. So this is going to be canceling with something before it that we can't see. Here we can see these cancel, and the n. If we wrote out more terms on the left, we would see that n minus 3 is going to cancel with something over here. And so there you go. We can clearly see we're left with the 1 over n and the 1 over n plus 1 here. So what we've got is S of n is 1 plus 1/2 minus 1 over n, which is so 3/2 minus 1 over n minus 1 over n plus 1. Okay, and so that's the beauty of a telescoping series, is this is the S of n, right? It's not easy finding S of n's for series. This is the S of n, and this is valid for all n going from 1 to infinity, because I mean this S of n is not, we could write this out for 1 trillion terms, and we know we would simplify to this. So, okay, all we need to do now is take the limit of this. We want to analyze this series. What is this limit? Well, this goes to 0, this goes to 0, so 3/2. This partial sum here, or no, this infinite sum here is equal to 3/2. Okay, same process. Let's separate this up using partial fraction decomposition. Okay, so 3 is equal to a times n plus 3 plus bn. When n is equal to 0, you've got 3a is equal to 3a is equal to 1. When n is equal to minus 3, you've got minus 3b is equal to 3, b is equal to minus 1. So this sum is equal to 1 over n minus, okay. So now let's write out the s of n. So we're starting at n is equal to 1. So we've got 1 minus 1/4 plus, when n is equal to 2, we've got plus, when n is equal to 3. And let me just write out a bunch of terms in case it's kind of complicated. 4, 5, okay. And so let's just see here. Is this kind of complicated? It looks like it is, unfortunately, kind of tricky. So let's go ahead and do another term, 1/6 plus 1/9. Okay, now let's do, just to make this really clear, let's go all the way back to n minus 4 so we can really get a good look at this. N minus 4 plus 3 is n minus 1. N minus 3, n minus 3 plus 3, n minus 2, n minus 1, and then the nth term. Okay. Yeah, this is, now we can get a really clear look at this. So, all right. The 1/4, those 1/4 go away. The 1/5 cancel. The 1/6 cancel. The 1/7 cancel. Yeah, this is confusing here. So let's actually do this. Let's actually, so we'll say plus 1/8 plus 1/11 plus 1/9 plus 1/12 plus, like that, okay? So we can see the, or no, this is minus. And these are minuses in here. Okay, the 1/8 cancel, the 1/9 cancel. Okay, and so we want to expand it out a good bit because we've got, like, we're dealing with potential terms that don't get canceled for the first 3 n's. But we can see, like, if we expand this out really big, then when we're far enough away from the n's, we've got full terms canceling for sure. This cancels fully, this cancels, all of these cancel fully. We can't see the 1/10 canceling because that's going to come, that would be next, right? The 1/10 would come next. So we know it's going to cancel, we know it's going to cancel. Everything away from the n's is going to cancel. Okay, and so now if we look here, we've got, let's see, the n minus 1s go away. What am I doing? These are minuses. Okay, let's see. Yeah, you can't see. It's going to parallel this. So it's going to be these last 3 terms are going to have leftover terms. We know these are going to cancel. Okay, and so let's see what we've got. we know, so this is going n minus 1, then n plus 1. So we're going to have an n minus 2 over here, a minus n minus 2 over here. Oh, and this, okay, yeah, oh, here we go. 1 over n, minus 1 over n plus 1 over n. And there we go. That's what we're left with. You see how it's kind of, they mirror each other? This term, and this term. So like the first term, 2, 3, 4, 5. The first term and the fifth term. Now counting from this in the first term, third term, and the fifth term. So S sub n is 1 plus 1/2 plus 1/3 minus there you go. Pretty cool, right? Okay, now if you take the limit as n goes to infinity of this, these go to 0, and so we just have 1/2 plus 1 plus 1/3. So it's 3/2 plus 1/3. So 3 over 3 times 3 over 2 is, and then, so 11/6. Right? Once we got the S sub n for n is all real numbers, just we're home free in terms of analyzing the series. Okay, so let's bring this over here, and so we've got, I'm not sure, I would think it'd be nice if we could take the natural log of each term of the sequence. Yeah, if we could take like the natural log, then we could get rid of those e's for the time being. But to do that, we have to say that this is equal to a number. Then we could take the natural log. And the only way we'd have to determine that this was definitely convergent. And we can't really do that. We don't have a way of doing that. We could determine that it could be convergent if we took the limit of this sequence and we saw it went to 0, then it might be, the series might be convergent, but we don't know for sure. And it is a property of a series that, so if you've got a sequence, if you have a sequence, the natural log of a sequence, you can do that. You take the natural log of every term. So let's that seems a little too advanced for this where we're at in the book right now. So I'm not sure if that's what they're expecting us to do. Let's just, okay, e to the 1 over n. Well, let's come to just to the side for a second here. So the a sub n is e to the 1 over n minus, and then can we separate this e to the 1 over n plus 1? No, we can't. So okay, let's just write out some of the first terms. So S sub n is, we're starting at 1, so e minus e to the 1/2. Yeah, this should just be a normal telescoping series. So e to the 1/2 minus e to the 1/3, e to the 1/3 minus e to the 1/4, e to the 1/4 minus e to the 1/5 plus e to the 1/5 minus e to the 1/6. All right. Okay, let's go just n minus 3. E to the 1 over n minus 3 minus e to the, it would be 1 over n minus 2, e to the 1 over n minus 2 minus 2 plus 1 plus e 1 over n minus 1 minus e to the 1 over n plus, and then the nth term. Okay, is that right? Minus 3 plus 1 is minus 2. Yeah, okay, so what we've got is these cancel, so this is a simpler one. Didn't necessarily need to write out all these terms. So we can see these are going to cancel, these are going to cancel, these are going to cancel, this would cancel with the one before it. And so the S of n is equal to E minus, okay, so what is the limit as n approaches infinity of S of n? E, this approaches, 1 over n plus 1 approaches 0, e to the 0 approaches 1, so e minus 1. This is equal to e minus 1.